Hey guys, welcome to today. We're going to introduce redesign of a robotic gripper finger. We will separate our presentation for two main parts. Firstly, we're going to recap the product we chose, and then we'll discuss our product redesign. The robotic gripper finger is used as a part of robotic gripper for pickup. The primary customer is electronic and technology industry, and the secondary customer is medical and cosmetics industry. This is a component of the gripper.
For the functional analysis, the primary function of the finger is to grip objects. To do so, it needs to stabilize objects, which can be done by increased friction and exert pressure, and contact objects, which can be done by transmit motion through allowing rotation and translation, and transmit power. To assure dependability, it needs to stabilize the structure. Finally, it needs interchangeable attachment to enhance product. For the function component mapping, the plastic grip piece is used to exert pressure and serve as an interchangeable attachment.
These are two of the assembly sequences that we considered. The first one is bottom up and the second one is delayed cover placement. We determined that bottom up was the better sequence to follow.
Here's the bill of materials for our finger gripper assembly. You can see that we have a total estimated cost of $32 for the entire assembly. We then took those components and organized them by their costs and their relative functional importance, organized in this table here.
Here is a functional differentiation table. The only difference is in the interchangeable attachment function. And here is the differences highlighted between the primary and secondary varieties. Here is the original assembly sequence we had, but using delayed differentiation and moving the assembly of the plastic grip piece towards the end of the sequence, we get this modified assembly sequence.
For the manual assembly redesign, the total assemble time before the redesign is about 140 seconds, and the cost is about 0.8 per part. For the module part, we chose to redesign the plastic grip part. This is a comparison of before and after the redesign. The redesign features are shown here. The fillet structure is extended for easy insertion, and we chose to use the snap bit instead of screws to decrease the assemble time and part counts. We also added a rib structure to facilitate orientation. For the platform part, we choose to redesign the top cover. This is a comparison of before and after the redesign. The redesign features are shown here. We combined the pin structure into the part to reduce the number of parts. We added the ribs as a locating feature and added chamfer for easy insertion. After redesign, we decreased the assemble time by 25 seconds and the cost by $0.15 per part.
Comparing the before and after cost for manual assembly, we estimated a decrease of about 14 cents after the redesign. The redesigned assemblies were designed to have no impact on the product functionality, although the increased complexity may increase the manufacturing costs. Next, we chose to automate a subassembly of the robotic gripper, which was one of the joints of the gripper. We estimated the cost to be about 26 cents for the automated assembly. Here are the before and after views of the automated assembly. You can see that we have three main changes to the inner support brace to lower assembly costs. Where in this case, A is the removal of the inner brace cover piece, B is the removed section at the far end of the piece, and C, which is on the back end here, is a groove that we added. At A, we removed the hole in the support brace and removed the cover piece to simplify the design by decreasing the part count to reduce costs. The removal of material at B was done to give the support brace an axis of symmetry to reduce handling costs. And finally, the groove at C was added to give the support brace a locating feature, making automated handling easier. After redesign, the total cost for assembly was roughly 20 cents per part. Comparing the two costs, the redesign reduced the cost by about 6 cents, or by about 23%. The removal of the inner brace cover was based on our functional component mapping matrix, in which it did not serve any of the important product functions.
Some of the most important dimensions are related to the snap fit, and there's also this rib piece that is used to better align this piece during assembly of the part, and we selected a tolerance of plus or minus 0.1 millimeters. Another part we redesigned for assembly is the inner support brace. Some of the key dimensions are things like the hole size and the distance between the holes, as that is the way that parts are connected to each other. And if the dimensions are slightly off, the overall assembly might not fit together properly. And so we've chosen a tolerance of plus or minus 0.1 millimeters for this part. In terms of selecting a manufacturing process for each of these parts, we went through a process of creating a matrix and considering factors such as the material, shape, mass, minimum section thickness, the tolerance, the surface finish / roughness, and also the economic batch size. And here is the matrix completed for the plastic grip piece part. There were two candidate manufacturing processes, machining and injection molding, and we decided to select injection molding. Here is the same manufacturing process matrix completed for the inner support brace part. From the results of considering all these different factors, we selected machining as the best manufacturing process.
To get the suggestions of redesigning for injection molding, we first used DfM Pro, and it suggested that we should add draft angle and unify the wall thickness. We added 3 features for better manufacturing of injection molding, and this is the comparison of before and after the DfM. The redesigned features are shown here. The thickness of 3 rib structure are reduced to 60% of wall thickness to avoid shrinkage. And we added filler to avoid some sharp corners, and the 2-degree draft angle is added on the rib structure in the bottom. And these are some key dimensions after the redesign.
Design for manufacturing. So we start with the machining of the inner support brace, and we calculated the material cost and the non-productive time. Then we went and filled out the Excel sheet and calculated the time for machining the feature, and the total cost came out to be $4.91 per part. Then we did some redesign with DfM Pro. We basically fixed out an error that was marking by drilling 4 holes instead of 2. And then we did some redesign, and here are the key dimensions for that. Here's a comparison of the 2 before and after. And here's the things that we changed. So we first added a flat surface so it's easier to clamp the piece down. We also added more uniform radiuses of 6 millimeters, so that way we reduce the amount of tools that we use. And then we also created a feature where it's a semicircle instead of a flat surface, so that way the tool only has to go through once. And here's the cost estimation for the redesigned part. We went and calculated material cost, non-productive time, and the time to machine everything, and total cost came down to $4.64 per part. So we reduced the cost without changing any other functionality. And then Hubs has lower prices, and we think this is because we didn't choose the most optimal operations for the machining process.
As for the post-DFA part of plastic grip piece cost estimation, the total cost is $1.182 USD.
To get the suggestions of redesigning for injection molding, we first used DfM Pro, and it suggested that we should add draft angle and unify the wall thickness. We added 3 features for better manufacturing of injection molding, and this is the comparison of before and after the DfM. The redesigned features are shown here. The thickness of 3 rib structure are reduced to 60% of wall thickness to avoid shrinkage. And we added filler to avoid some sharp corners, and the 2-degree draft angle is added on the rib structure in the bottom. And these are some key dimensions after the redesign.
After redesign cost estimation, it is $1.139 in total. We reduced the material, and it also lowered down the injection fill time. The draft angle added also reduced the surface on the core plate. We want to build a good connection with our customers and also want it to be more environmental friendly. Our product service system will let our customers choose the plastic grip piece, and they can replace them without using screws and screwdriver or send the grip back for reassembly. That reduces the use of fasteners and transporting waste. To sum up, the benefits we gain include DFA saves 0.143 and 0.06 in manual and automatic assembly. In DFM, we save 0.313. The advantage is that manufacturing and assembly processes become easier and reduce their cost. However, it will actually increase the weight to the inner brace. If we can start over again, we will decrease the part count at the joints of the gripper finger. Thank you.